How skyscrapers stand during earthquakes. Welcome back to Blueprint to Reality, the channel where extreme forces meet intelligent design. When the ground shakes violently, one question always comes up. How do skyscrapers stay standing during earthquakes? Today, we'll uncover the hidden engineering systems that allow buildings hundreds of meters tall to survive nature's most violent movements. Introduction. Earthquakes don't push buildings gently. They shake the ground in all directions at once. Yet modern skyscrapers sway without collapsing, absorb massive energy, protect lives inside. In this video we'll explore what earthquakes actually do to buildings, why flexibility matters more than stiffness, the structural systems that save skyscrapers, and how engineers design for controlled movement. 1. What earthquakes do to buildings? During an earthquake, the ground moves suddenly, the building's mass resists motion, inertia creates powerful horizontal forces. The taller the building, the greater the forces. 2. Why skyscrapers don't fight earthquakes. The biggest mistake is trying to resist earthquakes with stiffness alone. Engineering principle. Rigid buildings crack, flexible buildings survive. Skyscrapers are designed to move, not stand still. 3. Base shear and overturning forces. Earthquake forces create base shear at ground level, overturning moments at the foundation. If these forces aren't controlled, collapse occurs. 4. The role of mass and period. Tall buildings have long natural periods. Why this helps? Earthquake energy often targets short periods, longer period structures experience reduced forces. Height can be an advantage when properly designed. 5. Structural systems that resist earthquakes. Moment-resisting frames allow controlled bending without failure. Shear walls provide stiffness and strength. Braced frames use triangular systems to control lateral movement. Most skyscrapers combine multiple systems. 6. Energy dissipation. Letting earthquakes loose. Modern buildings absorb energy. Techniques. Yielding steel members, viscous dampers, friction dampers. Energy is converted into heat instead of damage. 7. Base isolation. Decoupling the building. Some skyscrapers float on isolation systems. How base isolation works. Rubber bearings or sliders separate building from ground. Ground moves. Building moves less. This dramatically reduces seismic force transmission. 8. Tuned mass dampers in skyscrapers. At the top of many tall buildings sits a massive weight. Purpose. Moves opposite to building sway, cancels out motion, improves comfort and safety. Famous examples include Taipei 101. 9. Foundation design in seismic zones. Foundations must resist uplift, prevent sliding, handle soil movement. Soil structure interaction is critical during earthquakes. 10. Performance-based earthquake design. Modern skyscrapers are not just designed to survive. Design goals. Minor earthquakes, no damage. Moderate earthquakes, reparable damage. Major earthquakes, no collapse. Life safety comes first. Conclusion. Skyscrapers don't survive earthquakes by being rigid. They survive by flexing intelligently, absorbing energy, controlling movement. Earthquake-resistant design is not about strength alone. It's about controlled survival. If this video helped you understand seismic design, like, share, and subscribe to Blueprint to Reality. Comment below. Which extreme force should we explore next? At Blueprint to Reality, we design buildings to move so they don't fall. See you in the next video. Globe showing Europe-Africa building construction.